Stuart here. Today we're going to start a series of videos on domain-driven design, and I'm going to do them in PowerPoint, so I thought it would be nice to take the available PowerPoint line and shape styles and come up with some modeling notation that matches as much as we can the notation in UML. So here's a basic model that has a lot of our notational items on it. We have an aggregation. Customers belong to segments, but a customer and a segment can exist independent of each other. We have a composition, which is that an order belongs to a customer and an order detail belongs to an order. Those are compositions because the children can't exist separately of the parents. The order has an order status in C#. This would be an enumeration. And so we say that it uses order status. And order detail has a reference to a product. And we say that that is an association, that an order detail line is associated to a product. And of course, we have an interface in C# terms, and we say the lollipop is implements. It implements this particular contract. The tricky ones are aggregation and composition. So think of it this way. Composition is a must, and aggregation is a may. So if I have something that's aggregated, like customer and segment, then I can have a segment and I can have a customer, and there can be no relation between them. But I can also then relate a customer to a specific segment if I want. And if there is an intervening join table, we generally don't draw it, but then we would say that there's a many-to-many. A customer can belong to many segments, and a segment can have many customers. So that's an aggregation. Again, composition is a must exist. So an order detail must have an order as a parent. And usually when you're doing relational database modeling, you see the two things with different styles of foreign keys. One is an optional, one is a required. And we also see the association, which is just this points to that. And again, in relational databases, you can have a foreign key relationship, and it's the cardinality that's important. And also the direction of the relationship. And of course, a set, which in C# would be an enumeration. So far, so good. Here's an advanced example. So we have two abstract classes, purchase order and purchase order detail. They are very much a must-have relationship. In other words, PO detail can't exist without a purchase order. But we have an inheritance where we have gone from the generic type of purchase order, which in this case is abstract. It's abstract because we've got a dotted line around it, to a more specific set of classes. So we have equipment PO and software PO. They're different kinds of purchase orders. They probably extend the purchase order. And of course, we could have made purchase order I purchase order. But if we wanted concrete behavior in our purchase order, we probably have it as an abstract class. And when this is reified in the database, it may not actually physically exist. And we have covariance. And the explanation for that is that the equipment PO detail goes with the equipment PO in a must-have relationship, and software PO details go with a software PO, and that's a covariant relationship. And those are hard to set up in code, although you can using triggers on the database. You can if you have stored procedures that facade all the access to the tables, or if you have a view that does a join between equipment PO and equipment PO detail, and you always use that view as your entity in code. And so, again, we close out our notation by just calling out the composite relationship between parent and child as covariance of an inherited class. It's rare to see covariance without inheritance in the mix. I'm not even sure it's technically allowed. And you've got abstract and concrete classes with inheritance and interfaces with implements. So we're going to use this notation in the future lectures, and it just sort of sets the stage for how we're going to draw our domains and domain entities and relationships.